Hello physicists, in this video we're going to bring everything together and we're going to solve a brutal problem, right? And this problem is quite brutal, right? It's a bit redundant, but this problem is kind of hard. It is a tricky one because it's not really a level surface, but it's like it's sort of flat. It's angled. And that's what's difficult about it. And if you don't have a sense of what you are doing and how everything works in terms of the quantities and the methods involved, this problem is going to reveal those difficulties. It's going to expose the lack of knowledge that you might have, because this one's a very tricky one. And it involves trying to, like, if I were to kick a ball up an incline, okay, so let's say I have an incline. It's inclined at an angle beta, okay? So it's inclined at an angle beta above the horizontal. That's just the angle of inclination, just the angle of the incline, okay? And I kick the ball at an angle theta. I shouldn't have picked beta and theta, but we'll leave it. We'll just leave it like that. So if I kick the ball at an angle theta above the horizontal, note that theta has nothing to do with beta. They're two completely different values, and one does not necessarily have to equal or be the other, even though like theta is greater, because otherwise it's nonsense. Okay, so theta is the angle at which I kick a ball above the horizontal, and it follows its trajectory until it hits a point right over here. That is a distance r away from the initial point, and that distance along the incline will be r, and that'll be a range, and that will be the value that we're going to try to find in terms of theta, beta, and the initial velocity of the ball, v0. So, at first glance, I don't know what to do, okay? And you may not know what to do because there's so many things happening. Like, how am I supposed to find x? How am I supposed to find y? They're all variable. But if you have a good sense of how you go along solving these, then it's really not that hard. Now, first things first, let's write our x and y equations. So we're kicking the ball and it's projectile motions, so that means our x velocity will be constant. So delta x equals vxt. Delta x equals vxt. And the x direction is rightward. So you can't use delta x equals vxt to find r necessarily, okay? Because it's not in the x direction. Again, part of what makes this problem hard, okay? Now our y equations will be vfy equals v0y plus ayt. And we also have delta y equals v not yt plus 1/2 ayt squared. Okay, so we have all of our equations. And then you notice that we don't have a lot of the variables. Okay? But let's try to find the variables that we do know, especially Vx and V0y, because that's the easiest part. That's the easy part, finding V0y and V0x. Okay, so if I were to, let's go back here. If I were to have our initial velocity vector, V0, and angle theta, v0x will just be V naught cosine theta. And V naught y will just be V naught sine theta. V naught sine theta. So it means that these are the components, and we have just found out two of our missing pieces. Vx, which remains constant, which is V naught cosine theta, and V naught y, which is V naught sine theta. Now, let's see how we can use the principles that we use for our, I don't want to say but easy problems, and see how we can apply it to this problem as well. Now, we want to find time because time relates both of these equations. Now, which one of the equations can we use to find time? Should we use equation 1? Well, no, because we don't know VFY. Okay, it's not explicitly given to us. Should we use equation 2? No, because we don't know delta y. Okay, it's not explicitly given to us. Okay, so now we're stuck. We don't have a lot of the variables required, except we do. Because I said if you have an understanding of the general principles of how projectile motion works, you're actually given delta y and you're given delta x. Okay, you're given delta y and delta x, which is very, very convenient. How can we find delta y and delta x from the diagram here? All right, and you can pause and just try to think it out by yourself. All right, look at the diagram and see what quantity you can use to find which one of the given quantities that you can use to find delta y and delta x. Okay, now assuming that you've given it a try, what I want to do is I want to extend this and I want to draw a triangle here. And the reason I'm drawing this triangle is because, and in fact, we're moving from this height to this height, which means that this side length is our delta y. It is our delta y because we're changing that amount in terms of the height, in terms of, what happened? In terms of the y position. So it turns out that this vertical leg is delta y, and you can give a guess. You can probably guess what the delta x is. It'll be this horizontal leg of the right triangle, delta x, because we're moving from this x position to this x position. And that is really the heart of the problem. Knowing that delta x and delta y are really just the legs of this right triangle here. Now, how can we find delta x and delta y from our diagram? From the diagram we're given. Now, we have a right triangle, so that should immediately ring an alarm bell. And it's literally screaming, use trig, use trig, use trig. Okay, it's screaming for you to use trig because it's a right triangle and you're given the angle and you're given the hypotenuse. So the problem is to literally tell you, just use trig, use sine, use cosine. Okay? So delta y, we can see that delta y is equal to r times sine of beta. R times sine of beta. Okay? And delta x is r times cosine of beta. And you can verify these by just, writing the ratio and all that stuff. But this part is not hard. It's just trig. The hard part was the visualizing this right triangle. But now we have two expressions in terms of r. Okay, which is good because we're trying to solve for r. So now what we're going to do is try to solve for t. Okay. We're going to try to solve for t because now we have everything in terms of given quantities. So we just have to brute force this one. We're going to have to rely on pure brute force. Now, what can we do? Okay, what can we do? Now, delta y equals v naught y t plus 1/2 ayt squared. Right? Isn't that correct? That should be correct, right? Now, this gives us our sine of beta, that's delta y, equals v naught y, that's v naught sine theta t, v naught sine theta t, and we're going to use the magnitude of g, so we're going to include the direction as a minus sign, minus 1/2 gt squared. And now we run into problem number 2. You can't solve this equation. You can't, because we don't know time and we don't know r. We don't know time, we don't know r. And we have 2 unknowns in one equation. Okay? Remember but there's always hope. Because every problem's solvable, in my opinion. When you're given a problem, I always try to find a way that you can use what you're given in order to find some type of solution. Okay? And if you remember, I said the fact that these two both have r will be useful. You're probably right. You're probably thinking we should use that. We should use that relation. Okay? And we should use this relation that x and y also both have the variable t in them. They both have the variable t. So, what can we do? Now, surprising everyone, we're going to go to x now. We're going to forget y for a minute. We're going to forget y for a minute. And we're going to go straight to x. We know that delta x is r cosine of b. And vx is v naught cosine theta t. That means if we divide by v naught cosine theta, we get t is equal to r cosine beta over v naught cosine theta. Like this. And this is actually really significant. This is significant. Now we have an expression for t in terms of r. This is really good news. Because now we can substitute this expression for t inside this equation. Okay, see how we use the fact that both delta x and delta y have r in them, and both the equations for x and y have t in them, and we can use those two similarities to create and to establish a correlation. Okay, and this is basically the solution. Okay, now it's just a whole lot of algebra, which I know everyone loves here, by the way. Okay, so now we just have to solve our sine of beta. Now you have to really watch your algebra and prepared for a good showing of your algebra skills. Now, our sine of beta equals v naught sine of theta times r cosine beta over v naught cosine theta minus 1/2 g and all of this squared. And we have to solve for that, by the way. So I'm gonna leave that up to you, and I'm gonna end the video right now. Just kidding. We're gonna solve through this together, and we're gonna see how we can use our powers of algebra to simplify this expression for R as much as possible and to solve for R. Okay, now in this expression, you can see V naughts immediately cancel, and we can use the identity tangent of theta equals sine theta over cosine theta, which is a really important identity to learn, especially when you're dealing with trig expressions in physics. So this can be simplified to tangent of theta. So what we're left with is our sine of beta equals our cosine of beta tangent of theta minus this ungodly expression, g r squared cosine squared beta over 2v0 squared cosine squared theta. And now this is where we bring out our quadratic equations solving skills, again from algebra. So we want to solve for R. So because we don't have a constant term, it's actually not that hard. Okay, because we can bring all the R terms on the right hand side and factor out an R. So let's do that. Okay, let's do that. So we have R we're gonna write the this thing first. Okay, we're gonna you know what? What's much better? We're gonna bring the R squared term on the left, so it's positive, and I like positive terms, because then I don't have to be confused about the signs all the time. Okay, so we're gonna bring all the terms on the left hand side and solve this horrendously looking equation. Note in terms of R, and note how I'm already factoring out an R, so we have an actual constant term times R. That's a really good strategy to use if you think you're gonna get stuck with all the terms. You can group the terms together. See how I grouped these two together? Now I know this is all one constant. Okay, now we have R squared, we have R. So let's just factor out an R. Okay, let's just factor out an R. G cosine squared of beta over 2v0 squared cosine squared of theta times R plus sine beta minus cosine beta tangent of theta. That equals 0. So as a result, we get R equals 0. See, R equals 0? No. Okay. R equals 0 it corresponds to this point. We want to find this distance R. Okay, we want to find this distance R. So R equals 0 solves this equation, but it's not the one we're trying to find. We're trying to find the more complicated one. We're trying to find the inner expression. So now all we have to do is solve this inner expression for 0. Okay, and how do we do that, you might ask? Well, let's start. So I have G cosine squared beta over 2v0 squared cosine squared theta times R equals cosine beta tangent of theta minus sine beta. So now we can easily solve this equation for r. We can solve this equation for r by just multiplying. And we get the following expression. And it's quite complicated, but this, in essence, is our answer. Now, this part is kind of optional, but let's see how we can simplify it further. Now, let's distribute 1 cosine theta out of the cosine squared theta to the quantity in the parentheses. Cosine theta times cosine b cosine theta tangent theta minus sine beta cosine theta. G over g cosine squared of beta. Now note that from the identity tangent theta equals sine over cosine, this quantity is just sine. So that's just sine of theta. And what we get is this expression. And this is probably the most we can simplify it. 2v0 squared cosine theta. And this quantity in the parentheses is a trig identity. It is exactly a trig identity. Okay, it's the sign of a difference of angles. Okay, so if you know that trig identity, you can simplify even further. And you get this expression. This is probably the most you can simplify it. And this is our expression for the range R of a projectile shot at the base of an incline. And just one last aside. If beta is 0, then the incline essentially becomes a flat plane. And if you have seen the video on like 2D motion problems, especially the ones, the second problem regarding the range, if you plug in beta equals 0, you get the exact same answer. So you know that it's correct for beta equals 0. And it is correct in general, because it doesn't seem like we've made any glaring algebra mistakes. So this is the range of a projectile fired from the base of an incline. It was a difficult problem, but brought together all the concepts that we had learned so far, as well as a lot of algebra and trigonometry. And it shows the power of trig in tandem with physics concepts. Alright, I think that this will be it for two-dimensional motion. We've basically analyzed all aspects of projectile motion. You literally use two equations in x direction and the y directions independently, and you can connect those two directions by time, and using that key strategy you can solve even problems like these, which seemed intimidating at first, but at the end proved to be not as big of a hassle. Thanks for watching. If you have any questions, just comment below. Okay, thank you again, and see you next time. Bye.